Okay, so in this video we just want to look at some really four basic function manipulations we can do to take a graph. If you think of a whole graph and want to move it around on the axes, how would you do that? Well, a good way to look at that is to look at sine of x. Okay, so we'll start there. But then what we want to do is take a times sine of, now this can vary, but I do it this way, so I'm going to say b times the quantity of x minus c, like that, and then plus d. And it says add sliders, add all. I'm going to add them all on there. And right now they're all set at 1, and we see that we got a slightly different picture here in blue. So what happened? Well, actually it was the C and the D that did that. I'm going to take these and have them so they can't move quite as much. I'm going to go between 2 and 2. Here for the C, and I'm going to start it at 0. And then also for the D, let's just go between -2 and 2 and start it at 0. And you see, if C and D are both 0 and A and B are both 1, then nothing changes. And what's nice about this is we can change each and every one of these one at a time to just kind of see what happens. So let's start actually with the D, and notice that as I move the D, see, it looks like I'm taking, even though you're doing this at each value of x, you're doing something a little different. It looks like I'm just taking this whole thing and lifting it up by making D more and more positive. And it looks like I'm taking that whole curve and moving it down by making D more and more negative. So there you go. That's what D does. And we can notice that if we change some of these other things, it actually does not lift up or move down the function here. So let's go to C, and as I move C, notice as I move C to the right, the graph moves to the right by that amount. Okay, so I have moved C by 1, and notice this point here becomes this point here at 1. There's 5, so that's 1. And if I move it in the negative direction, it comes back. And so what's important there is that this is a minus C. Okay, and that allows me to move this back and forth. Let's put it back at 0 here. And the easiest way is probably just type the 0 and put it back. Now, so I've been going in reverse order. Let's look at what happens with B. Actually, B, I think, is a little bit counterintuitive, maybe. Notice that as I increase B, what seems to be happening is I'm squashing the original curve. So B started out at 1. And that's the same. Now, as I make B bigger, it squashes the curve, and we can see that. And so a bigger B inside here makes this thing go more, it makes it skinnier, so to speak. You've kind of taken everything and squished it together. Okay, and if I come down here less than 1, between 0 and 1, what it's doing is it's stretching it out. All right, it's stretching it out. So there's 0.7, it has stretched that thing out. It's kind of grabbed the ends and pulled it out. So I can see that with the b equal 0.7. Now, if I take it to a negative, what happens is it does the same sort of either stretching or compressing, right? If it's bigger than 1, well, bigger than 1 in absolute value, then it kind of pushed it together. But notice that it also made its reflection with the y-axis. So when I put in the negative, right, I get its reflection across the y-axis. So if this is -1, that point there becomes that point there. This point here becomes that point there. It reflected it across the y-axis. So I can use a negative on the inside here to do that. Now notice I have the b times the quantity of x minus c, and that's important because if I go to 2, let's put a 2 up in here so we can compare that. So there's the original 2, but now notice when I shift this over, when I get to 1, it's still just moved over by 1. If I had bx and then minus just c all by itself without multiplying by the b, you wouldn't get that same sort of shifting property. It absolutely has to be in those parentheses like that to make this still work nicely. I mean, you can figure out how much it should shift if you have the bx and then just minus c without b times that. You can still figure it out. You can, say, well, okay, I want to shift it by 1. Well, I've got to take into account the b and all that. It's just too hard. It hurts my brain. And so, I just write it this way, and then it works out beautifully. So if I take it up here to shifting by 2, all right, there, that point that was at the origin is now up here at the 2, and I can slide it back and get it back to the 0, and same thing in the negative direction. Okay, so that is why I write it with the b times the quantity x minus c. Okay, so let's get rid of that again, and we'll set b back to 1. And so finally, what happens here with the a is it stretches it up and down. So notice zeros are still zeros. So it's not that it shifted it, it stretched it. It took this point and pulled it up here away from the x-axis, and any point below the x-axis, it pulled it away by that same factor. And so it made it twice as tall, or here 4.4 times as tall. If I get it down to a 2, notice here the height is 1, there the height is 2. So I had it grow by a factor of 2. If I take it to a 3, then that was a 1, that's now a 3 up here. And that's still a 0 because 3 times 0 is 0. So A stretches it up this way. And sines and cosines, these periodic functions are really nice ones to use to look at the effects of this. And we'll show you why, because, whoops. So let me take something like, do the same sort of thing. We'll start with x squared. Okay, and now I'm going to take a times b times x minus c all squared. Okay, so I put that bx minus c all inside the squaring function, and then plus d. Okay, now I'm going to turn that off and turn that off so I can see, ooh, these are almost the same color. I can change that by going here, and let's make that orange. Done. Okay, so here's our original is blue, and here's the funny thing is look at what A does, right? A is supposed to be stretching it up. So, you know, let's, here's 1, 1. If I multiply by 3, I should get to 1, or actually negative 1, 1. Negative 1 and 3, and here's 1, 1, and then 1 and 3. So that did what it was supposed to do, and as I take it back, you see, you know, it goes back in. But what does it look like it's doing? It actually looks like it's squeezing it. Well, one could argue that to make it stretch up, that's what you're doing, is maybe squeezing it. You know, I don't know. But it's just that the mathematics works out to be kind of the same thing, because you know, let's do this. Okay, here's 3x squared. Now, if I take b and I start changing that, if I make that bigger, remember that squeezes in, and I get it to right there, and they're the same. Oh, b is about 1.7. See, here, 3x squared, when a was 3, I got this picture. Now, if I put a back to 1, but then b at 1.7, I get the same picture. Well, what happened? Well, the difference is, if I put that constant on the inside of the square, to get 3x squared, it would be the square root. So I start typing SQRT, and it makes a square root. Square root of 3, get this outside the square root, x, close that parenthesis, and then say squared, and that green one, oh, it's right there. And if you look here at what the square root of 3 is, so I'll come down here and say, what is the square root of 3? It's 1.73. And so this 1.7 was pretty close. If I go to 1.73 and turn this off, and turn the red one off, right? And then there's the orange one that shows up. And so it's doing the same thing that the sine functions did up here. You know, the A, the B, the C, the D are all working the same way. Again, if I, let's take B back to 1 and start with our x squared. And so I have my x squared, and this is x squared because A is 1, B is 1, C is 0, D is 1. But once again, if I can raise this thing up simply by adding in the D. Now that doesn't change with these functions no matter what. That's always going to work nicely, is just raising the function up, because it's outside of everything. Well, let me try to get this. I'm not very good at getting, oh, there we go, 0. It's outside of all this other stuff always, and so it just runs up and down like this. Then now what about the C? If I start moving C, remember that's supposed to move it left and right. And again, actually that works very nicely. Okay, so the C works nicely and the D work nicely. So moving up and down and side to side work quite well. -0, that's happy with that, I guess. I'll get rid of the, I'm not happy with it. I don't like the looks of that. So, so there we have the C. So the C and D work nicely, but the A and B, depending on what your function is, they can look a lot like each other. You can possibly achieve similar results by either messing with A or messing with B, but not always. In the sine function, that certainly wasn't true. Cosine, that wouldn't be true. So it really depends a lot on the function. And now let's I want to do something just slightly different here, and what I want to do is take this x squared, I'm going to put in here f of x equals, and then we'll just do something like a 3x squared plus 1 divided by x. Okay, so we get this really funny looking thing here. Okay, nifty looking function. But now what I'm going to do here is get rid of that square, and I'm going to put in here a times f of x. Oh, I gotta get rid of, there we go, a times f of b minus or b times x minus c plus d. I'll get rid of these things here. But notice, right, a is 1, b is 1, c is 0, d is 0, and the orange is sitting right on top of the blue. And remember what these things do. C moves it side to side. So I take this and look at that. It moves side to side so very nicely. Okay? And you see, I'm just doing it from the F, right? The symbolic notation. So I can take this symbolic notation and tell you what I might not even know what this curve looks like, but if I look at this and you tell me the values of A, B, C, and D, I can tell you what happened to that curve. And so that's a pretty neat thing with these 4 transformations. So let's get back to 0 here. So the side to side, again, that worked really nicely. Up and down, again, works very nicely. Now, with something that has a vertex like this, you can see the up and down very, very well. But if you look over here at this left-hand side, it's not so easy to tell that, oh, all you're doing is shifting the thing up and down. But that is actually what's happening. You know, in a way, to me, it looks more like a string on a guitar or something that's vibrating back and forth, but actually it's shifting up and down. But it's hard to see without a vertice, you know, and again, that's why the sine function is so nice to kind of see what's going on, because the vertex helps you in that way. So let's get back to d equals 0, and now let's mess with the amplitude, or scaling this thing up and down, you know, from the x-axis. And as I scale it, right, I make it bigger. Notice, you know, the vertex is jumping up by whatever factor it needs to jump up, but this place where it crossed the x-axis at 0, it's not changing. You know, its location doesn't change at all, and that's because we're just multiplying everything by some number. I can turn it upside down by making that a negative, and so there, you know, if I make it -1, I get a mirror image across the x-axis, so that's nice. Again, 0 is 0. Now if I set this back to +1 and I go mess with the B part, now B again made it skinnier or wider relative to the y-axis, and again if I go to B equal -1, it should make the mirror image across the y-axis, and it did. Okay, so even though I'm using this f of x to do this, I can tell you exactly, you know, if you tell me b is -1, I can tell you, oh, it's going to give a mirror image across the y-axis. And you know, Desmos is just great for seeing that, and to see that, you know, you can think of this f of x as a whole set of points that just gets transformed by this algebraic sort of transformation down here. Okay, and we've got 4 things we can do again, and you know, the -1 was nice in that it allowed me to get that mirror image. But if I go up here to, again, something between 0 and 1 should make it wider, and it does. But notice, as long as I'm positive, nothing over here crosses into the negative region over here, because it's still all going to be positive. And so we're just stretching it or compressing it relative to the y-axis. Okay, so 0.8, it stretched it out a little bit. If I go up here to 1.6, it squeezed it in toward the y-axis a little bit. Everything got squeezed in. Okay, so that's the idea. And again, you know, this, we can just work with this notation that, you know I've got a set of points here. What do I want to do with it? And if I say, well, I would like to make it half as tall, so I'm going to do 0.5 times f. I would like to make it twice as wide, so that's actually, instead of a 2, if I want to make it twice as wide, I need a 0.5 or 1 over 2 times x minus c. Now I'm going to move it to the left by 1, and so I have to, I have to subtract a -1, so I'm going to do a -1 there. So I move it left by 1, and I am going to move it up by 3, so plus 3. And get rid of that because it's just getting in our way of seeing. But so here was the original, and now here is how I moved it. And again, remember it said I made it, let me make that a little wider so we can see the whole thing. Okay, so what I wanted to do was I wanted to make it half as tall. Well, it looks taller. Well, remember, I added 3, so get rid of that for a moment. I made it half as tall. Okay, now I'll put that 3 back in. So I made it half as tall. Then I wanted to expand it. I wanted to make it wider by 2. I wanted to make it twice as wide. And notice this. This is much wider than that, twice as wide, but I had to use the reciprocal 1 over 2. Then I wanted to move it to the left by 1, so I had to do minus a -1. Now I could just put a plus in there, and that moved it to the left by 1. And then I wanted to raise it up by 3, and so I did that. Now why I wanted to do that, I don't know. It just seemed like the thing to do. But that's the idea, and I can do it here with the f of x notation. Once I've, if I've defined f of x, or if you just give me a picture of it, I could kind of sketch about what it should do. Okay, so this is this idea of kind of these 4 parameters or 4 constants. I'll call them parameters. Parameters, you kind of think of, they're constants that you might change a little bit. So they're not exactly variables, but you might want to change them somewhat. And so those are parameters, and we can use those parameters to move a function around. So there we go. That's our 4-parameter transformation stuff. Sorry to get technical there.